Yeah, my name is Roly Perera. I work at the Institute of Computing for Climate Science. I work with Dominic. Oh, that's the end of my talk, not the beginning of my talk. If only. Okay, so I'm going to mention some collaborators as I go forward, but I just want to shout out these three people in particular because they've done a lot of the implementation work over the last few months and years, and some of the organisations that have funded and supported this work. So when we communicate climate science, we rely on charts, text, and other summaries. And this paints a high-level picture, if we're lucky, but the relationship to the evidence base is quite unclear. It's often not clear what data I'm looking at, how these conclusions were reached, and so on. And if I want to dig further into this myself, then I have a very difficult problem. The data availability is going to be very sparse, and what to actually do with the data is going to be very hard as well. And there may be some text that helps me understand what I'm looking at, but that text is going to have that same kind of problem as well. There's going to be all kinds of science and numbers scattered throughout the text, but it's going to be unclear where these things actually come from. So one way to frame this problem is to think of it as a disconnect between the world in which we do science and the world in which we communicate science. And computational notebooks like MIST and Jupyter are a kind of step towards bringing these two worlds together, but they have quite a few shortcomings. The cells still execute as black boxes. They have a very flat structure, and the decomposition of the pipeline or the workflow into cells is determined by the author rather than by the reader. Now, I'm not proposing in this research to address all these issues with notebooks. Our contribution in this space is a language called Fluid, which we describe as a transparent programming language. So what I mean by that is a language that tracks how data flows through the computation and then is able to automatically enrich outputs with queries that allow a reader to explore the provenance of what they're looking at. And these are a couple of papers that we've written on the kind of theory, if you like, that underpins this language. So what I'm going to try and accomplish in this talk today is just present a simple example that we've started working on recently of applying this to a real policy document. So normally I cherry pick my examples to show our language working at its best. So this is very much not in that space. So I'm going to highlight some of the difficulties to do with our implementation, but also the kind of data quality issues that come up in reproducing this kind of thing, and mention some of the ways in which we're going to address some of these challenges going forward. So what we've been looking at is this independent assessment of the National Adaptation Programme, NAP3. So this was produced by the Climate Change Committee. So this is an independent advisory body that advises the UK government on resilience. So in other words, how well the UK is able to kind of be resilient in the face of climate change. So, and this is a project with a couple of collaborators at Bristol. It's very early stages, and this will probably feed into some of the other projects that I'm going to talk about at the moment, but so far it's a kind of standalone activity. So let me show you what this looks like when we try to sort of reproduce this in Fluid. So, okay, so this climate change risk assessment, CCRA3, identified 61 risks and opportunities for the UK relating to climate change. And this report then evaluates this NAP3 programme, which has a bunch of commitments for activities and actions rather that the government's going to take. And it evaluates those commitments to see how well they address the risks and opportunities that were identified in the CCRA report. So what we have here is a couple of figures with a caveat that we've reproduced from the report. So the figure on the left is figure 1 in the report, slightly altered, and the figure on the right is a figure from the Excel spreadsheet containing the data for the report. So when we implement this in Fluid, what we get is a kind of transparent version of these figures. So what that means is we can access a view of the underlying data on the left, and then we can interact with parts of the output and get a view of the inputs that are relevant to that particular output selection. So as I move around in the output, I can see which parts of the data that I'm looking at. So if you look on the left, you'll see that these data sets are actually quite a bit larger than what we're looking at here. So there's about 5,000 elements in the data here. And we're just looking at 5 rows in this case and 2 columns of a larger data set. Now, if I click on this purple segment here, then I'll see that some of those purple segments on the left have been highlighted as well. So the chart on the left, sorry, I should have explained, the chart on the right is showing actions from the original CCRA assessment organised by governmental department. The chart on the left is organising those same actions by chapter. So this highlights one of the data quality issues that I mentioned earlier, which is that this data set doesn't actually have the names of the chapters in the data set. So in the Excel spreadsheet where they computed these figures, they just used hard-coded ranges for the cells, essentially. And because the rows were sorted by chapter, that worked reasonably well as a way of aggregating the actions by chapter. But it's not a very data-driven approach. And in the kind of setup we have here, where we're trying to surface information from the data and the computation into the user interface to make it something more self-explanatory, that obviously doesn't help us because we can't surface information that isn't there. So in this case, we just don't have information about the chapter names. But I can tell you that chapter 7 is international dimensions, I think it's called. So if I put my mouse over that purple segment that was highlighted, I can see that there were 6 actions on the left that count as recognised but not addressed, associated with 4 risks from Chapter 7. And I can see the reason that these things were highlighted is that 3 of those 6 risks were assigned to DEFRA, and DEFRA was the government department that I selected on the right. So I'm able to see these overlapping data dependencies, and that explains why we get this kind of shared highlighting between outputs and inputs. So I can do that the other way around. I might pick, for example, Chapter 5, which I think is health, environment, and communities, or something like that. And then I can look at how that intersects with various government departments on the right. Okay, so as you can see, there's quite a lot of complexity in the user interface already in this simple example. So the claim here isn't that if you're a policymaker, your life is going to be radically easier on the basis of this. What I hope it does convey is the kinds of queries that we can support if we have this kind of infrastructure. Okay, so this is the code that we use to produce those visualizations. I don't have time to go into the syntax, but it's basically a Python-like pure functional language with first-class functions, lambdas, records and data types, list comprehensions, and other kind of familiar features. But the key takeaway is that the programmer doesn't have to think about any of those interactions I just showed you. They just describe how to map data to visual elements. The runtime analyzes dependencies and adds the interactions we just saw, and then the user can interact with the output to pose queries. So the second thing I want to show you now is something we call transparent text. So as I mentioned at the beginning, policy reports, scientific papers, and so on make a lot of the claims they make using text. But this text is very hard to interpret as well, in the same kind of way the charts are. There are things like graded adjectives, there's iteration, there are whole part relations, there's implicit reference, there are quantitative expressions all over the place. So the research question we're asking here is, can we enable this supporting text to be transparent in the same kind of way that I showed you a minute ago with visualizations, so that it can be data-driven, self-explanatory, and verifiable? So let me show you what that looks like in that example as well. So the way I'll do this is I will go to the fluid code, and I will just uncomment that block of code, and then I'm going to reload the example. Now, you'll see how long it takes to run the program and generate the dependence graph. It takes about 10 seconds. So that's one of the challenges for this research, is making it more efficient. But what we have now is some figures with some supporting text. we actually had this bit of text at the top here before, and I'll use that to show you what I mean by transparent text. So if I put my mouse over the number 61, we can see that's not just a literal in the text, it's actually being computed by a query over the data. And if we look at the code for this document, we can see that it was computed by calculating the length of the nub, meaning the kind of equivalence class of the risks, or rather the risks up to their name according to risk, or this risk or opportunity descriptor. And the reason for doing that comparison on risk or opportunity descriptor is so that when I put my mouse here, we actually see that data. Otherwise, if, for example, we just considered the length, then the actual name of the risk wouldn't be relevant. So this is a way of surfacing that information into the user interface. Now, you may have noticed there's a little underscore highlighting on the committee's priority risks down at the bottom. So if I click on this number 61 and then put my mouse here, we'll see that I can now see the priority risks as a subset of the overall set of risks. And this is something slightly different. This is what we call a link. So a link is a query that has a natural language label. So we calculate the query, but instead of presenting the result of the query, we just attach a string to that query. And then when I move my mouse over the string, then we run the query. And now I see the data that was needed in order to compute that result. So moving on, I might wonder what natural environment and infrastructure sectors means in the context of government departments. So if I interact with some of these action counts, then I can see that at a minimum, DEFRA, DESNES, and I think that's the Department of Levelling Up, are relevant because they've been highlighted on the right. And then finally, this 10% down here is a slightly more complicated calculation. It's computing a maximum, and this shows actually that the dependency information that we calculate is slightly incorrect here, because we're actually only seeing the data that was needed to compute the percentage of DEFRA's actions that were fully addressed, not the fact that DEFRA was the government department that happens to have the maximum. So that's just a shortcoming of our current dependency analysis and something that we need to address. But that gives you the idea of what we mean by transparent text. So let me just skip forward again. Okay, so the takeaway here is that, like visualizations, text can also be bidirectionally linked to related data. So there are three key ingredients to this. So first of all, transparent programming languages to make this information actually useful and provide the kind of interactions I just showed you. The second thing is what we call an interpretation assistant. So this is AI-based tooling to actually generate these programmatic interpretations. So if you wanted to write a substantial paper or a document in this sort of style, it would be quite laborious if you had to author everything by hand. And then the third component is a library of domain-specific and domain-general idioms for mapping data to textual content. And we've explored this in a recent paper that's under review at the moment, where we've looked at using LLMs to synthesize, given a document and given the data that the document purports to be about, synthesize expressions that replace certain quantitative or semi-quantitative expressions in natural language with code that computes them from the data. So we can think of this as happening at dissemination time. I might be a publisher or an author, and I want to produce a document that embeds the evidence base into the document. But interestingly, I think we can also think of it as something that happens at what you could call a simulation time. So I may just be a reader or a reviewer, and I'm trying to interpret a document in terms of the data, and I might want to retrofit that document with the computational interpretation as I go along. So I mentioned some of the challenges that come up in this approach. So there are some problems in the dependence graph as currently designed. We implemented something a few years ago that gives us a kind of more fine-grained dependency analysis and allows us to reach into kind of parts of larger structures. That turns out to be problematic. So I think we have some idea of how to fix it, but fixing it is going to introduce problems of its own. It's going to sort of broaden out the dependencies quite a lot. So I think we've got some techniques for how to deal with that. So that's what I'm referring to here with this idea of scoped queries and relative queries. And then to speed things up, we've got some ideas on how to use techniques, perhaps inspired by automatic differentiation for building the graph using compilation-based techniques. Okay, and then the other kind of aspect of improving the kind of correctness and performance of the system is, I think, moving the language closer to the problem domain. So, for example, having proper native dictionary comprehensions, kind of native multi-dimensional arrays and columnar operations. So you can, if you're a functional programmer, you'll be used to writing these sorts of things, perhaps using lists or something like that. When you're using a dependency tracking language, you want to have the kind of domain that you're using to express a solution to a problem to be as close as possible to the actual appropriate solution for the problem. Otherwise, you end up with a lot of noise and inefficiency. So I think the way we're thinking of this is as converging on a functional dialect of Python, which has a native query language. So the last challenge I want to mention are challenges around usability and interpretability. So one of the things I haven't had a chance to show is the ability to look at intermediate stages in the pipeline. So we saw that kind of input-output relationship before, but a lot of the interesting work that goes on in computational analysis is kind of in these intermediate steps that we often see in notebooks. So this is some work that we presented at the live workshop a couple of weeks ago, and we're now writing up in a paper which allows you to look at intermediate steps in a computation and also interact with those and look at the upstream and downstream provenance relationships. And then this second thing is something we call intentional provenance. So this will probably build on the improvements to the graph, dependency graph that I mentioned a minute ago. So this is the idea of enriching the provenance information with information about the actual operations that took place. So this on the left, this image is a screenshot. This is a mock-up on the right, inspired by spreadsheets. And again, this is a reason to produce this kind of interface. We would probably need the solution to be expressed in a language quite close to the problem domain. So you would need things like columnar operations, pivoting, rolling up along a dimension, and so on. So if the program were expressed in this very kind of data transformational sense, then I think it's plausible that we could generate some kind of user interface like this. So that's where I'm going to stop. Thank you for your time.
Questions? Please, can you come out? It's for the recording later. So the mic is over here in the front.
Okay, this is really neat, thank you. I'm curious, can people hear me? Is this, or it's only for the recording? It's not. Is it only the recording and not? Testing.
Yeah.
Okay. So I'm curious what the scientists or the users have to say, right? So, did you start the project when they said to you, "Hey, we got to have more transparency. How can you help us?" What was the motivation, and how are they responding to these kinds of tools?
Yeah, that's a good question. It's very much the other way around. So it's more like, this would be a cool thing to do. Oh, why don't we also use it for transparency in data science? But more recently, we've started to speak to actual people interested in this kind of space. So that collaboration I mentioned, where we're looking at this policy document, that's a researcher who works in the climate space, in policy and risk adaptation in particular. So what we wanted to do there was pick an example that's actually quite hard for us in various ways, but potentially has an actual stakeholder or a user who cares about it. But that's a direction we've only really started pushing on recently.
Thank you.
Thanks.
Thanks, Roly. That was a really cool talk. Simon Payne-Jones is really proud of the fact that he put lambdas into Excel, and Excel is a really widely used tool. Have you considered kind of transpiling this into just a spreadsheet so that you can take advantage of all the data dependency stuff there?
Yeah, that's an interesting idea. So there's a project at Cambridge, actually, that Alan Blackwell, I can't remember the name of it. Do you know what I'm talking about? Yeah, so there's something, it's actually very cool, and I don't know whether they've implemented, it's a spreadsheet system essentially for visualization, where the visualizations themselves are kind of little spreadsheet type things. I've forgotten the name of the project, but And I don't know whether they've actually implemented that by taking some kind of open source spreadsheet and sort of hacking it, or whether they've just come up with some proof of concept of their own. But yeah, I think that's a really interesting idea. And I think where I was going towards the end with that mock-up, the more I kind of think about that mock-up, the more I'm kind of less interested in traditional programming languages, and the more appealing it seems to just think about sort of a data transformation language more natively, what that would look like, and a visual language, language that already has a visual presentation kind of built into it.